The power of a lens is defined as being 1 over the focal length. And if you want to have your units in diopters, then the focal length is measured in meters. Now, whether you've got diopters or not depends on the question. In this case, you do have diopters, so you're dealing with meters all the time. Well, the focal length is 1 over the power. And because it's 1 over 2 and we're dealing with meters, then you get F is 0.5 meters. Now, of course, that's 50 centimeters. It then says when an object is placed at a distance 25 centimeters from the glasses, describe the image produced. Now, the person is using reading glasses, and it's correcting long sight. Now, with long sight, the person can see objects at infinity when parallel rays come in. That's not the problem. The problem is that when you look at near objects, the rays of light diverge much more significantly, and the person has a problem in bending the rays enough, and that is why you have to have this positive power. It's going to be referring to a convex lens, and a biconvex lens, for example, would be that shape. So these have got the so-called positive powers. They're converging lenses. Well, the lens we're going to use is a positive lens, a converging lens, and what you've got to do is imagine that you've got this converging lens with a focal length of 50 centimeters, and then you put an object 25 centimeters away from this lens. I've drawn a little diagram of it. There's the positive lens, the converging lens. There's the object 25 centimeters away, and there's the focal length of the lens itself, 50 centimeters. And you'll recall that when you have this situation, you draw a ray parallel to the principal axis. It goes through the focal point. That's 50 centimeters on the other side. One through the optical center, carries straight on, and the rays diverge. You therefore need an observer, an eye lens. And then your brain does a little construction. It assumes these rays have gone in straight lines and have come from there. If you do a similar construction for rays of light which come from there, they will appear to come from there, and so on. Now, they don't come from here. There's no light there at all. They appear to come from there. So this is a virtual upright image. And in fact, if you put your numbers in, you'll find that the image will be at the focal point on the same side as of the lens as the object. 1 over 25, 1 over u plus 1 over v is 1 over f, and v comes out as being, well, it's minus, which indicates it's a virtual image, but it's 50 centimeters away from the lens, so it's there. Well, you've basically got to describe that image, and once you realize what they're talking about, then it's not so bad. Of course, the lens itself is going to be on your nose in front of your eye. So there's the observer normally drawn, but in actual fact, this lens will be absolutely right next to it. Well, an object placed between the lens and the focal point, which is what we've got here, produces a virtual, magnified, upright image. In other words, you're really getting your glasses lens to act as a magnifying glass. Now, when it comes to the calculations, I think it's probably best just simply to learn the formulae. I'm not very good at learning these formulae. I tend to sort of derive them when I need to. But you don't want to do that under the pressure of exam conditions. So for long sight, hypermetropia, these are the formulae you need to know. If you want to correct your eyesight, then 1 over the focal length of the corrective lens, in other words, the power of the corrective lens, is given by 1 over the required near point. Now, the near point that you normally are said to need is a 25 centimeter near point. That's regarded as normal. You subtract from that 1 over your actual near point. Now, you'll find out in just a moment that the actual near point of the person is 50 centimeters, which is far too far away. Anyway, that's the formula. Learn it like a parrot and then simply put your numbers in. There's the required near point, 0.25. In fact, it says that you've got this object at 25 centimeters. There's the actual near point that you've got, and there's the corrective lens there. And the near point comes out as being 0.5 meters or 50 centimeters. They're going to want the units in. What you then learn is that if you then put your glasses on, it messes up your far point. Now, normally, if you've got long sight, your far point is at infinity. You can see parallel rays, you can focus them without any difficulty at all. But the problem is that when you put your glasses on, you mess that far point up. So learn like a parrot that if you put your glasses on, this is your new far point. Used to be infinity, this is what it is now. It turns out that it's actually 1 over the focal length of your corrective lens. Now, the focal length of the corrective lens, as we know, is 50 centimeters or 0.5 meters. So that goes in there. And that means your far point is half a meter or 50 centimeters. It used to be infinity. So once you've done your little calculations, in go your answers. Without the glasses, your near point was 50. That was the top calculation. And then with the glasses, your new far point, it used to be infinity, it's now 50 centimeters. In the notes, those formulae are derived, but I wouldn't do the derivations. I would learn the final result. Part B then goes on to talk about a diverging lens. And they simply want the ray diagram. They don't want you to actually describe the image, particularly just simply to construct the diagram. And it's a fairly straightforward exercise. There's your object, and you draw a ray parallel. It gets diverged, and where that ray will appear to come from is the focal point, which is there. A ray through the optical centre, all of these are the same, they simply carry straight on. You can see straight away that the rays diverge, so therefore you need an eye to bring them together. Your brain then does its usual calculation. It assumes that ray and that ray have always gone in straight lines and will construct a situation where it will see those rays apparently coming from here. Now, they haven't come from there at all. They've come from there, but that's where your brain will imagine they've come from. If you did a similar construction with rays of light from here, they will appear to come from here, and you can construct where the image is. It's an optical illusion created by your brain, so it's virtual. You will notice that the rays from the top of the object, they're still at the top of the image, so the image is upright, and you can see that it's smaller than the object, so it's diminished. They don't ask you to describe it, they simply ask you to put an eye in the correct position, which obviously is there, but if they did ask you to describe it, it's virtual, diminished and upright. And all the ray diagrams for diverging lenses will give you that particular sort of image.